This is a small video that explains the difference between the composite beams and non-composite steel beams particularly. Let's go down to the structural engineering 101 when we used to design the basic, when you start designing concrete structures, the basics are equilibrium that this particular section of, let's say, a hinge beam, and this is the section, we assume that this is an equilibrium. This means that this is a assumed neutral axis, and if this is positive bending, then the section on this part, the top part is in compression and the bottom part is in tension. For equilibrium to be valid, summation of forces should be zero. That means that compression is equals to tension. This is a very simple, we will start with the very basic of a section design. And since this is concrete, let's take the area of this block B, and we use A because we don't know that what depth of this concrete block is participating in the compression. So this is A. Therefore, we use a safety factor of 0.85 multiplied by FC multiplied by the breadth of the section and the A, which is the depth. So this is the compression part. And the tension part, since we assume that the concrete will not take any tension and the only tension will be taken by the steel. And this, we assume that area of steel multiplied by its allowable stress, or the stress it can take, is tension. Hence, this equation becomes ASFY is equals to 0.85 FC prime B into A. Now, the only unknown in this equation is A. That we can find by simply equating ASFY over 0.85 FC dash and B. The purpose to start with this concrete example is to establish an understanding how C compression has to be equivalent to tension. Now let's look at the case of steel beams. Let's take a typical I section. Same beam we assume to be in the bending. Now again, this is going to be compression and this is going to be tension, and this is going to create the internal equilibrium of this section. In the case of concrete, concrete is not isotropic because the qualities, the properties of it in compression are not similar to its properties in tension. However, this is not the case in steel. Steel is similar in tension and compression. So C equals to T, and this time we don't have to have any A because it's pretty clear that this is going to balance out. So C is going to be ASFY, which is top, and ASFY, which is bottom. This is how the equation balances in the steel beam. Right. Now let's do this as a composite beam. You have a steel beam. And you have a deck on top, or let's say slab, which is, we'll discuss the shear studs in a while, and this is concrete. This is now a particular different case altogether. Now again, we are assuming that this is a certain level of composite action, whereas this concrete is going to be part of, is going to take part in resisting the compression and the tension. However, this, when we ask this to be composite, we usually assume this to be 50% composite, not 100%, maybe 40%. In very rare cases, this can be 100%, but we assume this to be a composite section. What is the scenario here now? Now we have 0.85 FC B and then A now, because since we have this concrete block, it's going to have an A value here. Plus, of course, the ASFY top is equals to now the ASFY bottom. You realize when you equate these equations, since you know that force is equal, stress is equals to force over area. If you want higher stress capacity, if you want this to go up, then this is inversely proportional to area. This goes up when this goes down. So if you have higher value of area contributing in the stress, you see that you will have higher allowable stresses. So that's how composite beams become more economical, because this particular deck, this particular section in concrete is taking part as a compression element. However, certain engineers that I've seen confuse this with something like this. They believe that if you have a beam like this and you put a simple tray, non-composite deck on top, and you pour in concrete over here, this is composite. No, it's not. This is not composite. The reason is that there is no shear transfer between this beam and this concrete. This concrete is not becoming a part of this top part of the steel beam to take compression. As a matter of fact, this can be seen as a UDL on top of this beam. So it's an added load. This is obviously, when you're designing this beam, let's say of a span 20, let's say this is a 20 feet span. If it's a composite beam, obviously when concrete is participating in the stress and you have a higher value of bottom area in tension, you have a higher area in tension, then this becomes economical. We'll see in a bit how economical, and this scenario is uneconomical. This is not a composite beam. Let's discuss shear studs or shear connectors or shear transfer in a steel beam to actually act like a composite beam. This is your beam. This is your steel beam. And if it starts to take a bending form like this, and it's bending like this flange, this is going to exert a compressive force on top. Now, if you have shear connectors here, there's a whole design guide on this. What these connectors do, that they transfer shear the load to the concrete slab. So if you don't have these shear connectors connected to this beam rigidly and have the shear capacity to transfer their transference load, the shear load on these concrete element, it's not a composite beam. So if you think that you're putting a deck on top, a deck like this, and maybe screwing it like this is not a composite beam. If you think you can just weld a bolt here with manual welding, that again is very difficult to achieve. It has a very lower value of composite. These kind of welded board, what is the percentage of composite, 20 or 30 or 40? It's difficult to determine when these welded bolts. Well, there are some guidelines on this, but the real way of doing this is welding the shear connectors to the beam. Here are some pictures that you can see that show you the type of composite beams that matter. What we have done in Pakistan for a while is SCIP or ICF flooring system. How do we achieve composite beam? Is simple. This is an I section. And we have our SCIP panel here. The details on that you can see in the link below. You have a SCIP panel here. And this is just the insulation material. This has no contribution whatsoever to the structural value. And then we pour concrete here. We then very clearly weld some rings here. Here you can see in the picture. And these rings are the shear transfer mechanism that turn this entire section into a compression element and then this into a tension element. So if you have a typical beam, maybe the neutral axis is here, but if you have this composite beam, the neutral axis goes up and you have more area to resist in tension. So that's how the SCIP or ICF flooring system works in composite. And according to the ASC 7 research papers, we achieve up to 50 to 60% composite beam action through this process. Now, to verify to find out the percentage of how much is the difference between economy, I had a discussion with an engineer, he said 20%, but that's not true. If we have a very simple software called ASDIP, which we use for design of composite beams, and it just gives you a comparison between the capacities. So if I have taken a section, let's say it's a W18 by 35, it's a pin beam, 20 feet, it will give me, if I just take, let's say even 30% composite action, you can see that The design moment strength I get for non-composite is 249. And if I do the composite action, I get a capacity of 364. That's a lot of capacity. 249 divided by 364. That's almost 46%. So that's a lot of saving we do when we do ICF flooring systems or composite flooring systems. And it's very much evident over here. You can see the strength. You can use any software you want and you'll see the same section, same forces, same span. If you just pull out composite action, you get almost 40 to 50% increment in the strength and the capacity of the beam. And you do it the regular way, non-composite flooring systems, that is probably 1/3 less strength, even more than that, you have to compromise. So why not choose a composite flooring system, reduce the steel structure, section sizes, and the weight of the building. Apart from this,